Okay. Works. This is 1-1. Oh, cool, works. Okay, so we're ready to go. Sorry for the delay. Yeah, dark. Better? No, better. I don't know. No, don't know which is better. Middle. This one is not as bright as I would like it to be, but at least it's big now. Thank you. Did you do this?
Yeah, I kind of just like forced it.
Thank you. I mean, extra credit for helping everyone, for helping the class. It's a fair thing. Thank you. Okay, so what we're gonna do today is actually there will be a little bit of magic, which unless I probably advertise, you don't even think it's magic. But what we'll design today is memory, right? So everything what we've seen before was called this combinational circuit, right? So kind of easy. So you have those logical gates, right? And whatever you compose out of them. And if you provide some inputs, you know, sooner or later, and there is some delay, right? But sooner or later, you will get something as an output, right? And we've seen how we can construct something like addition operation and even the core of the microprocessor, which is the CPU, right? Or not CPU, but ALU, and arithmetical and logical unit. And that's nice, but there is still some gap, right? And you kind of feel probably the gap that you still don't understand how to build real complex logic out of it. And the problem here is that you have to somehow synchronize large digital circuits, right? Because imagine it's just a giant, you know, array of those gates, and they kind of live their life, and the signal propagates with the delay. Inputs and outputs are changing, but you cannot really like achieve a stable state, right? And for that, we will introduce this idea, which is kind of essential for building circuits which have memory and then scaling them, essentially combining circuits by attaching a tiny memory in front of a combinational circuit. So let me first introduce the idea of a clock signal. So at a high level, it's just a signal which oscillates between the high voltage V and a zero here, right? And we talked about it, like we talked many times about the cycle, right? And so the cycle is just this period of time between the two rising edges of this signal, right? And so if we say, okay, maybe this is a 2 nanoseconds, if we divide 1 by 2 nanoseconds, we'll get the frequency of our machine, which is 2 gigahertz, right? That's how they are related, right? And at a high level, what we want to do is to make sure that we will fit combinational circuit, and everything what it has to compute has to be computed within a cycle. So by the end of the cycle, it reaches a stable output. And then we will design a tiny memory, which we'll put here between the combinational circuit and the next combinational circuit to make sure that this memory will remember the output of the circuit. Let me just explain it a little bit better. So this is this terminology. So this is cycle time, rising clock edge, falling clock edge, and this relation. So here it's instead of 2 nanoseconds, it's what? Picosecond. No, I understand that picoseconds, but why is it picoseconds? Oh, yeah, I was wrong. You're right. So in my equation, it's actually not 2 nanoseconds and 0.5 nanoseconds, which is 500 picoseconds to give us the frequency of frequency of 2 gigahertz. And here they say, okay, look, it's half of that, so 250 picoseconds or 0.25 nanoseconds, right? And that gives us a frequency of 4 gigahertz. But okay, so back to this idea which I was trying to explain. So our goal is to enable composition of these combinational circuits, right? So essentially, imagine there is some logic. So maybe there is an ALU here sitting, right, which we designed last time. And maybe it will receive some inputs, something like, I don't know, 7 and 5. In binary form, obviously, it's like, it will be like 32 different signals, right? Each one which will be either 0 or 1. But if we represent it as a decimal number, let's imagine it's 5, right? And then it takes some time for this guy to, to compute this result, right? And the idea which we're trying to achieve here is in front of every combinational circuit, we'll put a specific circuit which is called a latch. And today I'm gonna explain how those latches are designed and why they work in a specific manner. And at a high level, what latch is doing, a latch, or it's called a flip-flop, it's slightly different things, but we will understand the difference by the end of this lecture. At a high level, it will remember its inputs at the rising edge of the cycle. And then it will keep them stable for the entire duration of the cycle until the next rising edge. So what does it give us, right? So imagine if we're adding this 7 and 5, and maybe it produces a result, which is 12, right? And maybe, like somewhere half the cycle, this result 12 is ready, which means that if we have a circuit just connected straight to it, and maybe it's like something like we trying to implement some operation on a program counter, for example, right? So maybe we're adding program counter with this output of this addition 12. Maybe it's branch relative branch instruction, right? So branch when equal, for example, right? So our intent is to obviously add this 12, right? So our intent to do 12. But unless we insert another latch here and make sure that we remember this 12 on the next rising clock of a cycle, the next cycle, then maybe this combinational circuit, which is here, maybe it will receive some different inputs. Maybe it will receive something like 11 and 10, right? And maybe this output, which in our case, we wish it to be 12 for the duration of next cycle, will start changing. And maybe some pins of this output, like this 32 pins or 32 signals, which represent 12 as a 32-bit number, will flip from 0 to 1, and maybe it becomes like 13 or 17 or something like that, right? So in general, if you just connect this to two combinational circuits like that, there is a very low probability that the output of the first combinational circuit will remain stable for just enough duration of time to make sure that the second combinational circle will produce something what you want, right? However, if you introduce those memories in between them, you will achieve what you need, right? So because you say, well, imagine we had this 7 and 5 here, right? So for the duration of a cycle, this addition was working, and somewhere like half of this cycle, or maybe 3/4 of the cycle, the result 12 became stable. Remember how we designed addition, this ripple carry manner. So because definitely we first compute the 0-bit, then the 1-bit, then the 2-bit, and all that this is a simplified view of an addition, right? So there are ways to essentially compute it much faster. You see that no matter what, this signal, the final result does not show up immediately on the output, right? So it takes some time. So however, if we choose the cycle in such a manner that for any combinational circuit which we use in this machine, we give it enough time to converge to a stable output. And if we ensure that this memory, which is implemented as a latch, provides the stable output or stable input like 7 and 5 for the duration of the entire cycle, then we will produce a stable result 12. And in the next cycle, when this changes to 10 and 11, right? And it only changes on the rising edge of the clock, right? And the clock cycle is actually provided as input to those memories, right? So the clock doesn't play a role inside the combinational circuit. It only it's only essential for those memories, which when the edge goes up, they will remember the new input. So for example, when we produce 12, and imagine for the duration of this first cycle, it's still 12, then the rising edge of the clock happens. This 12 is remembered here, and is for the entire duration of this cycle, this input for this combinational circuit remains 12, right? And this way you can essentially compose things. Question?
People are designing what make the clock based on the slowest.
The shortest. Yeah, I mean, first of all, I'm not an expert on clocking methodology yet. It might be a little bit harder than we naively can think about it. But a naive understanding is that you essentially take the smallest the longest combinational circuit and make sure that it will produce the stable output by the end of the cycle. You can play tricks with half cycles, and it's done as well. We'll see later how operations on registers can be, because the logic is so short that you can play it and say, I for sure know that by the end of this half cycle, result will be stable. And so you can do that as well. But I'm pretty sure that clocking is a whole business on its own. And people from electrical engineering, they probably know a lot more about it. But at a high level, yes. Question.
So the first latch, it's meant to like catch flow, so you don't have to output. Or the second latch?
Yeah.
What is the purpose of the first?
So just a second. So in this drawing, we have two bits of logic. So maybe think of it as maybe just for the sake of example, maybe you're implementing something like branch when equal, right? And maybe you have two registers S0 and S1, right? And maybe this piece of logic implements this comparison. So essentially does a subtraction, right, between the two registers, and 7 and 5 are these inputs from these two registers. Registers can be implemented as latches, right? So they will provide a stable input. And for example, this second circuit implements something like operation on the program counter, because depending on, like, maybe you also produce the output is whether it's 0 or 1, because you did the comparison. If it's equal, then it's definitely or like if you did the comparison as S0 minus S1. Oops, I'm kidding it. S0 minus S1, you produce 0, and depending on whether it's 0 or 1, this logic essentially, it's another ALU here, which essentially takes program counter and does this operation which we were doing something. For example, it shifts this value which will provide as a relative jump address, right? Shift by 2, multiplying it by 4, and adds it to the PC, right? So essentially, it's 2 bits of logic, and you can say, I can maybe fit them together and implement them as a single combinational circuit, and that's okay, but that will make your cycle larger, right? But then on the other hand, you say, okay, maybe I can split them and execute them in 2 consecutive cycles, and we'll use this latch as a memory between them. And towards the end of this lecture, we will get to the idea of finite state machines. And what is a finite state machine? It's kind of a funky name, but imagine you're writing a C program, which you can say struct state or C++. And whatever you have here, int A, int B, whatever. And then essentially your program or your CPU is designed as an operation on this state. So essentially say at every rising edge of a clock, I will kind of invoke a function kind of process. And this function process is like a tiny bit of logic which has to finish and then update the state back, right? And then on the, like maybe A changes from 0 to 1, B changes, or maybe B is unchanged, right? But you can see how now like there's a certain connection. So if I say like writing a CPU in a high level language, you can write it like that. And in a low level language, which is very low, right? For example, you can implement it in the same manner. So you say that the moment you have state and you can do operations on the state, maybe short operations, you can see how you can compute anything you like. You can build ALUs on top of that. You can build anything, any complex logic, essentially. I don't know, branch prediction by accumulating information about taken and non-taken branches in your program. You can remember them in some state. And when you see a new branch, you can say, okay, I'll predict that this branch will be taken. So, but that's how you essentially structure those systems. So I'll get to that in a second. Any other questions about this idea of latches? So let me now what we will do next is that we will understand what kind of a circuit can implement this latch for us, what kind of circuit implements in memory. But essentially, this is essentially what I was trying to explain you just a second ago answering this question. So if up until now, we learn how to build these combinational circuits, right? And how do we build them? Do you guys remember still? How do we get to gates? What's the process? We did last time.
Just like with transistor.
No, like imagine I want to build a function, some function. So how do I turn this function into gates? Like everything in machine is gates, right? Remember we started with this transistor, which is either in a conducting state, depending on whether you provide input here or not, right? So it's an inverter. If you say if the voltage is high, then here it's 0, right? Because it turns and conducts. And then from this transistor, you can build OR gates. And I didn't explain how, but just trust me, electrical engineers know how to do that. OR and inverter, right? And from these guys, we built what? Remember? So essentially, we use Boolean logic to implement functions. So in one, like if this combinational circuits that has two inputs, A and B, and an output, for example, E, right? Remember what we did? We did a truth table is one way to approach it. So we say like on these two inputs, E is 1, on this one is 0, on this one is 1, and on this, whatever, the last one, all combinations. And essentially you say, if this is my desired function, and we practice how to use it for the addition, right, for a single bit addition, then it's easy. You convert it into this sum of product term, and then you can easily build the gates out of it, right? Or alternatively, sometimes you don't even have to go through the logical, through the truth table, but you say, well, I kind of know the dependency. It's like A, I don't know, and not A plus whatever, A and B, something like that. And I'm not saying that it's the same as this one, but you might observe it from real life that this is how you want this to be connected, and you can write an equation immediately and just write it as implement it as gates, right? So, and now what we've learned is that a combinational circuit is simply the function of its inputs. But now what we say that one of these or some subset of these inputs can be the state, which we'll keep around. And it can be a large, but it can be like a more complicated state, like as complicated as you want, right? And what happens is that in order to maintain the state, we essentially provide a clock signal to this part of the circuit, right? And then combinational circuit takes the state, maybe some additional inputs here, produces the outputs by updating essentially the state again, right? And this is how we can essentially scale the system. Okay, so now let's try to build this latch. So this circuit, which is here on the diagram, is called an SR or set reset latch. Let's just try to understand what it does. So it has two inputs, R and S. One is called set, one is called reset, and the output Q and the inverted signal of Q. Let's just for a sec let's just stare at it and understand what happens when we, for example, provide 0 and 1 here, right? So this is a NOR gate, right? So it does an OR and then inverts the signal. So no matter what kind of value we have here, we can call it X, for example. If we have 1 as an input, what will be output here? No, before the inversion. From the OR gate, it will be 1, right? And after inversion, it will be 0, right? I agree. So we'll have 0 here. So since we provided 0 here as well, so 0 and 0, what do we have here? We have 1 here, and it happened to be 1, right? So at this point, this 1 matches this 1 over here, right? What happens if we suddenly invert this and we provide 0 and 1? You see that this is a symmetrical thing. Yeah, so it flips. So what we will have, Q will be what? Q is 0, Q inverted is 1, right? It used to be 0 and 1, right? Okay, cool. So this is set means that we will set Q to 1, and reset means that we will reset as 1 means that we'll set the Q to 0, right? Now let's see whether this circuit remembers something. So imagine the following input. Imagine we have the input 0 and 1, sorry, and we're changing this back to 0. So right now the inputs will be, let me just maybe change the color for a sec. If we have 0 and 0, and imagine right before that the signal was 0 and 1, and the Q was 1 here, right? So if we switching to 0 and 0, then what happens to this circuit? Who can help me? It stays the same. So do we see this? Right, so if the 1 comes back here, this one is 1, this input is 0, right? And so it's the total is 1, this one is still 0. We're passing 0 back here, right? So 0 plus 0 is 0, inverted is 1. So it remembers the state 1, right? So if I first set it in a state 0, so R equals to 0, S equals to 1. So at this point, Q becomes 1, right? And if I change S to 0, then Q remains 1. This one is remaining 0, right? So it remembered this 1. And vice versa, so if you essentially, if it was in the opposite state, if Q was actually 1, right? Let's convince ourselves that this is true. Let me just change the color again to green. And so if the Q was 0, right? Then this signal is 0. We're providing still 0 here, right? So it was originally it was 0, 1, but this one stays 0, and here we start providing 0 as well. So this is 0 plus 0 is 0, inverted is 1. 1 comes here. This one is 0. So 0 and 1, 0 or 1 is 1, inverted stays 0, right? Agree? Did I convince you, or was it too fast? And if we provide an input which is 1, 1, the circuit will be oscillating actually back and forth. So this input is considered invalid, right? But if we essentially, what we can do here is that we can set Q to 1 or set Q to 0, and then we can remember it for a while by flipping both signals to 0, right? Okay, so what does it give us? It will give us the following functionality. which we will call a D latch. Change the color back to red. So now we have two signals, two inputs, a clock, which goes like this, right? And so on. And we have the data, which we want to remember. So, and inside we have this RS latch, which we just looked at, right? So let's see what happens when the clock is high. When the clock is 1, we providing D in its straight form here, and this is inverted D, right? So if the clock is high, then this one is D and 1. D and 1 is what? Huh? D, remember this laws, so this will be D. And 1 and not D. Well, let's imagine, just for the sake of an argument, let's imagine D is 1, just for the sake of it. Then this one is inverted D is 0, right? So it's AND, so this one is 0, and this one is 1 and 1 is 1, right? So 0 and 1, remember what it means for the Q? It sets the Q, so it's the set combination for this RS latch, right? So imagine now, so while the clock is high, so here, and if D is 0, just for the sake of it, just check that we're right. So if this D is 0, right? So then this one is 0. So this output will be 0, right? Not 1, but 0. D is 0 is inverted will be 1. Clock is high, 1 and 1 is 1 here, right? And so what we have here is this 1 and 0, right? So it's a resetting signal which sets this guy to 0, right? So which kind of means that it's true for both. So if D is 1, then we will have 1 here, which is D. If D is 0, we'll have 0 here, which is also D, right? As long as the clock is high. Do you agree with this? Again? We can go again. Yeah.
Is not Q even used, or do we just take it on?
We typically don't use not Q. So shall I go again to convince you that this works as intended? Right? One more time. Okay, let's do one more time. So just again, let's switch back to our favorite thread because that thread was unsuccessful. So let's first consider the case when the clock is high, right? So the clock is high. So this is the clock signal. It goes up and down. Then when the clock is high, this one is 1. Imagine that for a second that D is 1 as well, right? So if D is 1, then this input is 1, clock is 1, right? So this is an AND circuit. So this one is also 1, right? So since it's inverted D, we'll get 0 here, and 0 and 1 is 0, right? And the input to our RS latch is 0 and 1, right? And just a second ago, I convinced you that we can go again through this, but if this is the combination essentially, which when set is high, which is this one, 1 is stored as Q, right? So it's a combination to store, just to set Q to 1. And we can go quickly, like again, through what it means. So this one is 1, this one is X. So X or 1 is 1. So this output is 0. This input is 0. 0 or 0 is 0. So this one is 1, right? And so Q is 1. Agree with this? Right? Now let's switch. Let me change the color to blue. Let's switch D to 0, right? So clock stays the same. This one stays the same. Oh, pardon. So this one is 0. So this one becomes 1. So this is 1. So this is 0 and clock is still high. So 0 and 1 is 0. And 1 and 1 is 1, right? And this combination 1 and 0 is a reset combination which sets Q to actually 0, right? So which means that it's, if the clock is high, this one is D, right? Again, it's like we can prove it by the truth table, but we can probably like think of it as well. So now let's see what happens when the clock is low, right? So when the clock drops to low, let me just again change color to green. So clock is 0 now, right? So this signal is 0. So no matter which signal we have here, X, right? 0 and X will always be 0, right? So this input is 0. And since the clock is low, it's also 0 here, right? So no matter what we have here, what kind of X we have, 0 and X is always 0. And remember that these two zeros is a remember combination for this RS latch. So it means that this D will continue being D here on the output, right? So what did we achieve suddenly? So we achieved the following logic with this, putting those ANDs with a clock here. So what we achieve is this. So if D is changing, like this output D will be changing for as long as clock is high. The moment it drops to 0, we'll remember this latest value of D, right? So and this D will be, like this latch will be in the remember state for the entire duration of this half cycle, right? So this is kind of nice. It's not yet what we wanted to achieve because we say, look, we wanted to remember on the rising edge of the clock. And here we're remembering on for the entire duration for as long as the clock is high, right? So we still need to fix this circuit a little bit to make sure that it only remembers on the rising edge, right? But at least it remembers something.
So in this circuit, that means we can only read during the latter half of the cycle.
Like this is the latch, right? So this is my 5, right? So that's 1 bit of 5, for example. So which and this, if this bit was, for example, was computed, maybe there was like some complex ALU in front of it, right? In front of this D latch, and this is 1 bit which was connected. Imagine it's bit 22, for example, was connected to the input as instead of this data, right? So and maybe it was like 0, 1, 0, 0, 1, 1, 1, because it stabilizes here because the rest of the circuit was moving forward, right? And at this point, it remembers as 1, and this becomes a stable input for this. The duration of the half cycle, this 1 becomes stable, right? That's what we do. And yeah, it's input to the whatever we kind of, maybe it's another ALU here, or maybe it's some simpler logic, maybe it's just whatever, a logical signal, whether it's addition or subtraction, like a carry signal or something, right? But this is how it will work. Agreed? So any other questions about it?
Back on the SR latch, we mentioned a minute ago that D latch were only really concerned with output. In this case, also, we sometimes care about
let's assume, I don't think you will care about not Q at this point. Let's assume like the way we use it, right? So we just want either set Q or reset, and this circuit allows us to essentially say this is my data signal, and I will set this latch to remember the data for the duration of low clock, so half cycle. Right? So, and this is kind of clever, right? So, and if you think about it, you can come up with those tricks yourself, but nevertheless, you know, it looks kind of elegant to me. And let me now introduce you how to build the latch, which is called a D flip-flop, which essentially remembers something on the rising, or more specifically in our example, on the falling edge of the cycle. So if you connect them, these two D latches, again, we have a data signal, we have a clock, and this is a D latch connected to another D latch, right? And we have a gain Q and not Q, which we don't care about much, right? And this is an inverter which inverts the clock signal. Let's see how it works, right? Let me erase everything for a sec. Oh. So if the clock is high, right? So we're here, the clock is high, right? We just agreed that we will be remembering this D here, right? Maybe D is changing, like maybe it's 0, then 1, and again 0, then 1, and stay stable 1, 1, 1, right? So this output of it will be D, right? It will be remembered right at this point, right? Where the clock falls down, right? And exactly at this point, since we're inverting this clock signal here, right? This clock becomes high, right? So this becomes high. So this is how this guy will see the clock, right? For the second latch. So this is latch 1, this is latch 2. So since D is already here, it will see D right here, right? And it will, since D is stable for the duration of this half cycle, right? This will remain D for the entire duration of this high clock, right? Agree? And so the output of this circuit will become D, right? So at what point we actually did remember, who can tell me at what point we actually recorded D, this D, which comes in here, at what point? So imagine this is A, this is B, this is C, and this is point E, and whatever, F. At what point we remembered? At C? No, it's not at C. Remember, D gets as an input to the first latch. The first latch remembers D for as long as the clock signal is high, right? So, like, imagine it's changing. It's like 0, then 1, then 0, then 1, 1, 1. And it stays 1 here. And then if it flips to 0 again here, we don't care because the clock went down, right? So this first latch remembers at exactly when we transitioned from the high clock to the low, right?
Sorry, I thought we were talking about the second.
No, yeah, we're talking about this D. We're talking about this D. But see what's happening here. So since this D got remembered on this falling edge of the clock, right, and stays stable into the second latch, this latch sees it always as D because it's not even changing for this latch. But the clock is high for this latch, right? This is where it remembers it, right? So the first kind of like on the falling edge, the first one stabilizes. And the second latch always sees this value for the entire duration of this half clock, right? When the clock is low, because for this second latch, the clock is high, right? So at what point we remember D then? At point B, right? So someone is shy, but that's correct. Because this specific organization of this, the flip-flop remembers the value when the edge is dropping here. Confused?
What is going on in between?
Like this D, which is an input in terms of D, or in terms of what? In terms of D, like this output, let's call it like Q prime, for example, it can oscillate, it can whatever, since the clock is high, this D latch, which we discussed right here, right? For as long as the clock is high, it will reflect, this data will be reflected here, right? So if data flips from 0 to 1 with a minimal delay of like a couple of quarters of picosecond, it will change here, right? So the same happens here. So the clock is high for the first duration of a cycle. So this value D is reflected as Q prime, right? But the moment the clock goes down, Q prime stays stable. And this Q prime serves as an input to the second latch, right? And for this latch, the clock is high exactly at this moment. So it will remember it and will propagate it here, right? And when the clock actually went down, this D still stays. So essentially, it remembers the value of D here, and it will keep it for the duration of the entire cycle, right? That's kind of ingenious, right? So build this tiny little trick, which essentially the first one kind of pre-filters this value, and the second keeps it, just because the first one doesn't allow it to change. Right? Okay, now it's clear. So, and if I ask you, what if we want to remember something instead of a falling edge, if we want to do it with a rising edge, what would we do with this circuit? Exactly, we can just simply invert the clock signal. But it probably doesn't matter, like in terms of clocking, but if you really want, and this is what we're going to be discussing, like by inverting this clock signal here, you will achieve this functionality.
Can you just move this knot that you already have inside the lat or the flip-flop to the other branch of the clock?
Can you move this one to here?
Yes. How would it do it?
Yeah, because it's kind of your. So if you put if you put this one here, which means that double inversion means straight line, and yeah, you can do it. It's the same equivalent. Right. Any other questions? So latches and flip-flops. So this is kind of your memory, right? So this is how we're going to build this tiny yellow component, right? And I said that in many, like I keep saying clutch, and I will continue saying clutch. Although in practice, I think any real machine will use this flip-flop. But in many cases, it's just fine as well, because as long as your like latch will, if you achieve a stable state within a half cycle, then the latch will remember it for the next half cycle. So as long as you like your logic here fits in a half cycle and produces a stable output, then it's fine to have a latch here. But in practice, we will always be using a flip-flop. Right? So, but now we kind of like, we got this idea that we can put the flip-flop, the flip-flop in front of a combinational circuit. It will provide a clock signal here. And on the rising edge, whatever the inputs are, they'll get remembered for the duration of the entire cycle, and only like it will change its value only on the next rising edge, right? Okay, so back to this idea that we can kind of think of this computers as high-level C programs in a way, right? Because I mean, I don't know, like state machine, that sounds a little scary, but in practice, it's very, very easy, as I was kind of telling you in a second. So, right, so what we have here is that, again, we can implement any state, right? We can remember as a group of those flip-flops. To remember the state, we need to provide a clock signal here, right? And we can essentially like design it as a function which updates the state. I can write something back here, and a function which again takes this state and produces some output, which will go and maybe like will be combined with another, like, you know, another state here, right? And those are the inputs maybe from some other circuit which lives over here as well, right? So, and my goal at a high level is to convince you that you can build any computation as a collection of those state machines. And probably this idea is natural to you, especially if you've been to these computer science classes, which discuss state machines. I don't know which ones did you cover. No, but what state machines did you guys? Yeah. So, and that's good enough. So, and you can build computation. You can build anything like, here's this like a state machine with a state diagram, right? So essentially, if you are in state 0. And you receive input like 1, you transition to state 1. It's, for example, what is this? It's probably something like a saturating counter. So essentially, no, actually, probably just essentially is because it can transition back to 0, right? But essentially, if your transition is, if you receive D1, you remember 1. If you receive 1 again, you stay in state 1. If you receive 0, you it works as a decrement. So essentially, it's like it's a saturating increment and decrement, right? So essentially, you can subtract, or you can provide 0 multiple times and you stay in 0, right? So kind of decrementing. And then if you see 1, you go to this state 1. And then again, if you see a bunch of 1s, you don't move anywhere. But then if you see 0, you move back to the original state, right? And you can build like, this is a saturating counter, or actually the counter which, for example, like if you're in state 0, you see occurrence of some event, so you move to state 1, you see 1 more, so you move to state 2, state 3, state 4, state 5, state 6, state 7, and if you see it again, like a saturating counter would leave you in this state, right? And if you don't see an event, for example, you can be moving backwards, but in this specific case, you overflow and you go back to 0, right? So that's a state machine. But okay, so what am I trying to explain here? That I'm trying to explain that think of it as a class. Like if you did some kind of a object-oriented programming, it's a class and a function which can execute something on that class, right? And you can combine classes in a way that you can pass fields from one class to another. So essentially connect multiple state machines together. And that's how you can build this computation in digital circuits. And eventually you'll, combining it with ALU, you can build a real tiny microprocessor, right? Okay, so any questions about memories and state machine? Everyone is looking at the clock. No, the clock is low still. It's not time to go. Okay, is that clear? Like what we did today? Okay, this is cool. So because look, so we started with digital bits of digital design. We built ALU. Now we understood how to remember the state in between, right? And our next step is essentially start building a tiny MIPS CPU, right? So let's start on this. So any questions before it while I'm transitioning to the next slide deck? Here I cannot. So okay, let's take a look at how can we build an actual machine which which executes the instructions which we want, right? So what we need to do is we need memory, right? Actually, I didn't explain how to build memory, so maybe I will try to explain next time. Like memory here will allow us to what? To store instructions, right? Let me just move this. And this is our program, right? Remember, we talked about it. It's the text of the program. There will be a data section as well, right? But everything is in memory, right? We will need a set of registers, right? Remember, to remember intermediate steps of the computation. And roughly speaking, and I hope I convinced you from the last time, that ALU is a kind of like a powerful mechanism which allows you to take registers as inputs and like update something on those registers, right? We can also, like, what did we build last time? We built addition, we built subtraction, we built set less than, we built branch when equal, stuff like that, right? Remember, what else is missing? What else do we need here for this machine to start running? Like, we need to remember this thing which was called program counter, which essentially points to the text of the program, and essentially this is where we get the next instruction from, right? So, but at a high level, this is more or less everything, right? Let's take a look. So if we combine those things, like again, this is our ALU at the very heart of it. We have memory here, so it's a data memory. And for now, for the sake of simplicity of an argument, let's imagine we have two separate memories: instruction memory and a data memory. In practice, it's implemented like that because you have a CPU and you have a caching hierarchy. And the way it works is that if you have a CPU here, like this, roughly speaking, it will talk to caches. And L1 caches, there is a separate L1 data and separate L1 instruction cache. And then below there will be L2 cache, which is already mixed and keeps both instructions and data. And under this will be, like, in most machines, there will be another cache, L3, and then this cache will go to memory, right? So in practice, when we talk about this memory, and you can build it as a real memory, like a DRAM, which is 200 cycles away, but in practice, you will always trying to access instruction and data memory as some kind of a local cache, which takes you like 2 to 3 cycles to access, right? And so if we do this on this diagram, right? So if we have a register, like for example, program counter, which says, okay, we will read an instruction from an address in memory, right? So program counter is kind of like an index into the memory array, right? So whatever the value is, maybe it's like, maybe it 0x101110, for example, right? So this instruction which sits here, we can provide it as input here, right? And there will be some control logic, which essentially, remember, our instructions now are encoded. So imagine it's an R style encoding. So it has an opcode, it has a function here, right? And if we use these bits of this function here and the opcode, right? And we can provide this control logic as an input to our ALU, we might decide whether we will do an addition here, or maybe a subtraction, or maybe some logical operation like an AND or a NOR, because like, or what else? We did NOR and we did NAND, right? So an ALU, remember, it takes carry and stuff like that as a control signal, and the operation as well, right? And then if we say, for example, maybe it's an addition operation. So some of this part of this instruction here, which is inside the opcode and a function, can be connected to the ALU here to specify whether it's an addition or subtraction. Some of this, like, what is it? Register source, register target, and register destination, right? So that can activate a specific subset of registers from the register file, and maybe this registers like S0 and S1 will be sent as an inputs to the ALU. ALU will do an addition on them, right? And if it's a register operation, it will update back the register. If it's a memory operation, like for example, maybe it's a load, then this ALU can compute an address, because remember, the way we do load is we write something like save the result into register S0, but use something like immediate value 55 and register S1, for example, right? And so here, for example, this ALU can actually do this addition. Like if we take out this bits of 55 out of this instruction and send them as input to this ALU, and this input, second input is register as 0, which we selected from the register file, this ALU will compute us the address, which is S1 plus 55, and we will, after some period of time, we'll get result back and put it into S0, for example, right? At a high level, it might work this way, right? And this is how we're going to build it. Yeah. And like, remember what happens, what needs to happen to the program counter register after every instruction? We do what? You add, yeah, so this is why it's, we have this another ALU here and stable input 4, constant input, which is always added to the program counter. And if it's just a regular instruction, this is the update to the program counter again, right? So PC plus 4. If it, however, is something like a branch, right? And again, after reading instruction from memory, right? Some of this bits from instruction can be connected to this ALU, right? And essentially what happens is that this input is PC plus 4, and this might be something like, if we do a jump, right? So maybe it's some kind of an address, like immediate address. Maybe again, we jump to something like 2000, right? So it will have 2000 X. So it will be PC plus 4 plus X, sorry, X 2000, right? And then this is how we will update our program counter again, right? So this is a very high level view of this CPU, right? So any questions right now? That's the way to construct it. That's one of the possible ways. Yeah, go ahead.
So a branch on equal would happen in the ALU on the right? So like farther down over the bottom.
All right.
Yeah.
Branch on equal.
Like the calculation happens in this ALU on the bottom right.
Mm-hmm.
And then that also needs to be able to change the program, right? So there shouldn't be any that goes to change.
There might be, let's drill down. So because let's gradually, what we're gonna do in the next couple of like minutes, we'll just essentially like zoom in and we'll see how branch equal is actually implemented, right? So for example, again, back to this R type instructions. So which like additions, which R1 equals to the value of R2 plus R3, for example, right? Or right. So if we have a register file which is implemented as a memory, right? So we can have 5 bits here as inputs to essentially select which register we want to read or write, right? And if there is like a separate port which allows you an update of a register, right? So what we get here on the output, so we get 2 values of the registers, for example. So we provide them as inputs to the ALU, right? And we have 4 bits to specify ALU operation, right? And the ALU will like either will provide the result of a 0, which might be used as a result of this branch on equal, right? Because that's what we want to do here, right? Or we can like get the ALU result itself, right? And so if we implement something like example of a load and store, right? So this ALU, which we're using, so again, same story, but we have registers as inputs, right? One register as an input and one constant immediate operand as an input, right? So it's again, so one of them will be a register, so R2, for example. So where does this come from? The second one. Yeah, tell me.
The constant gate.
Yeah, so it's, if we have this instruction here, right, and it's encoded in such a manner that there will be an opcode and there will be a constant 8 here, right? And a register, which essentially will, like, we will have two registers, like a source and a destination registers, although our RS, our source, our target, right, RT. So this one is, if I remember correctly, this one is what, R2, and in this example, and this one is R1, right, this one. And this 8 is taking the rest of this instruction. So this 8 bits are actually directly connected from the instruction, from the intermediate register, which contains the instruction, to this ALU, right? And so this will provide the computation will provide the address, right? And this address will essentially will be used as the input to the data memory. Then we'll, for example, this control signal, which is memory read, right, which we will activate based on the opcode of this instruction, right, will allow us to read from memory and get it here, and this will be connected back to the register file, and this is where we will come in and essentially update the register, right? All right, sorry, so specifically this one. Okay. So similar for the store, so if you have a store instruction, you will use this register as an input to the ALU. So R2, this 8 will come as a second input. It will provide an address as an output. So since we're doing a write, this will be connected to this register, which we read from the register file, which is R1 here, and we will activate this memory write signal. Right. So now let's take a look at how we implement this jump instruction. So we have this branch on equal, right? So we have to compare these two registers. So what we will do here is those registers will be sent as inputs, R1 and R2, to our ALU, right? This will only care about whether it's 0 or not. And remember, our ALU just separately compares whether it's 0. Remember there we had like this giant OR gate at the very exit of the ALU, and which we inverted here, right? Make sure that if any of them is 1, then this one is 1, and this one is 0. And if all of them are zeros, then this one is 0, and this one is 1, right? And so what we will do here, so we will take this 16 bits which are there in the instruction, which contain this offset. We will sign extend it, right? So because offset can be negative as well. So if it's negative, then it will be extended with 1s. And if it's positive, it will be extended with 0s. So we get 32-bit of an offset, right? Then since remember, we don't keep, since all the branches land on the addresses which are in the form of the last 2 bits are zeros, right? So whatever it's A, B, or C, D, the last 2 bits will always be 0, so we don't keep them. So that's why we shift by 2, right? So this is a logic before the ALU. So this one computes the PC plus 4 is already computed, like in any case, then we sign extend, do this computation, get the branch target, right? And so whether this branch is taken or not, we'll decide, for example, with this tiny multiplexer. Remember multiplexers, multiplexers, Max. So one will be just PC plus 4 here, and another will be this one, right? That's how you can organize. And then you pipe this back to the PC, right? So okay, let's take a look at how they do that here. So specifically exactly what we've done. So this one is PC here. This one is always PC plus 4. This one is this, from the instruction itself, we get this offset. We get this sign extended and to 32 bits, shift left by 2, right? So now everything is fine. So this ALU essentially adds PC plus 4 plus offset multiplied by 4. We provide it to the multiplexer, and this control signal, which should be connected kind of like this, will decide which one to use, right? But again, so it's actually believable that we can construct it, right? So like all these modules, we know how to build a multiplexer. ALU, shift left is also a simple function. Sign extend, like a little bit of logic, but not super hard, right? Just depending on whether it's negative or positive, it's extending with ones or zeros, right? Okay, so what we still we kind of didn't cover is how to build a memory, right? So I don't have time today, but we'll explain it next time. But if we zoom in slightly, so your control logic essentially becomes like this, right? So here you say if it's a 0, if the instruction is a branch and the condition has to be AND, right? It chooses this second output or second input to the multiplexer, right? So if it's like, what do we have to? So this is the ALU operation, right? Chooses like what kind of addition subtraction you have to do with the ALU. What else is interesting? So it's probably worth essentially next time, like it's worth stopping here and just essentially take bits of those individual instructions, which we take a look at the encoding, and we will make sure that those are actually the relevant bits, and they like this choose the register, like this choose the offset, and which we assign extend and stuff like that, right? And actually like everything will come together by like all the instruction encodings will come together along with this picture of the CPU. Okay, so let me stop here. So people are probably tired at this moment. So any questions?
So the shift left 2 before you add ALU on that top part, is that why, like when we're doing the encodings for our fields on the instructions, we divide by 4 because they're all already, it's hardwired to multiply by 4.
It is high-wired, but don't flip the reason. So the reason is that if this is the memory, and you say that all my instructions are aligned, right? They're aligned at 4-byte addresses. So all 4-byte addresses will be of a form of something like A, B, C, D, 0, 0. The next one will be A, B, C, D, E. Next one, right? Okay, it's not fair to say this, but essentially all of them will have because this is a hex and this is a binary, right? But all of them, each of these addresses, this one, and this one will have always the lowest 2 bits set to 0, right? That's why we said, okay, we don't really care to keep them inside the instruction, right? Because we know that they will be zeros anyway, right? So, and instead we keep those bits A, B, C, D, A, B, C, D, A, B, C, E, right? And then we essentially just add 2 zeros in the very low, in 2 low bits, right? So because by shifting left. And so this just implements our intent, right? we don't have to put it here. We can keep these zeros around and just nuke this component, but it's poor design, right? And ideally, we should just put it here. Okay, so I wanted to one announcement. I'm back. Oh, actually, I don't know. The idea was to, okay, like I'm still in a temporary office, and my office hours today are at 3:30 p.m. to 4:30, right? So please, if you have questions, come and talk to me. That's a good chance. My office, I forgot the number exactly, temporary, it's MEB on a 3rd floor. Thank you.